The first thing that I did in this one, because it ends up asking us about like, is the amount of water in the tank increasing at time equals 15, is I just took all of this information and I created a function that represents the amount of water in the tank. Because we have water being added as W of t, we have water being subtracted as R of t, we have that it starts out at time equals 0 with already 1,200 gallons in there. So putting all of that information together, I created for myself a function that I called A of t to be the amount of water in the tank. And again, it kind of has to take into account all of those things we just talked about. First of all, that we are currently starting with 1,200 gallons in our tank, and then starting at time equals 0, we have water dumping into the top, we have water draining out of somewhere, right? And we have to combine those two rates of change. And if we want to take our rates of change and go from that to an amount of water or just gallons, we would be talking about the area under that curve, right? So we'd be talking about the integral. Totaling up the amount of water would be the integral of that rate of change, and the rate of change is a combo of those two equations, and we would start at time equals 0, right, and it looks like we're going up to, well, some time equals x, right, or I guess I should say t. Now, this would be totaling up how much water would be put into our tank if I just made it W of t. But there's also water leaving the tank, so we would subtract what's leaving the tank, right? So I would subtract, this is what's being poured in, minus what's being taken out. And again, what I've noticed a lot of times is we are forgetting our variable of integration, dt, with respect to time. So the function we're looking at right now would tell us how much water is in our tank, right? That's the amount of water. The question is this function, is A of t, increasing or decreasing at time equals 15? And that goes back to just our underlying idea of calculus and what functions tell us things like increasing and decreasing. Go back to your justification sheet, right? On our justification sheet, we said that if something was increasing, we ideally looked at its derivative, right? And if its derivative was positive or the slopes of the tangent lines are positive, that supported the fact that my function was increasing. And if its derivatives or the slopes of the tangent line were negative, that meant that my function was decreasing. So what I would look at is the derivative of A of t. Okay, well, let's talk about the derivative of A of t. The derivative of A of t, first of all, the derivative of a constant is 0, right? And what's the derivative of our integral? What's inside the integral, right? So the derivative of A of t is just what's being added minus what's being subtracted. So let's pause there. Are we all okay with that? Yeah? And we want to know specifically what this is at time equals 15. So this is where we're going to grab our calculators. Now, guys, I'm going to tell you that you're going to end up doing a lot with these functions. You can type them in individually, but I would suggest typing them into like y1 and y2 because we're going to be typing these in several times over the next couple problems. So go ahead and type w into y1, type r into y2. I'm going to go grab my calculator and show you what I'm talking about here. Maybe. Now, careful when you type in the trig function. It is a sine squared. And so to type in a sine squared, I put a parentheses, I typed in sine, I put what was inside my sine function, and then I close the sine function parentheses, and then I close the parentheses I put before the sine, and then I squared it. So a double parentheses at the end there before you square. Otherwise, it's going to square the wrong piece of that. Same thing on the second one. We had a sine squared on r of t. So that's how you type a sine squared into your calculator. And like I said, we're going to use those several times, which is why I went ahead and just took the time to type them into y1 and y2. And remember some then shortcuts. If I'm going to evaluate this function multiple times for different reasons, we are currently evaluating at 15, right? So I want to know what y of 15 minus r of 15 is. If I want to evaluate a function at a specific value, I can go back up to alpha, trace, and it gives me that little shortcut menu, or you can go to your vars, yvars menu, and it is option 1. What that's doing is taking the function from y1. If I want to evaluate it at a specific value, I type in parentheses 15, and it's going to go plug 15 into what we have in y1. That's what we want, except for we also want y2, r of t evaluated at 15, so go grab y2, evaluate it at 15 also. And our calculator will do that for us a lot faster this way. Okay. And then we have to just interpret what that's telling us, okay? So if our derivative, which we just evaluated, comes out to negative 121.09, okay, let's answer the question. The question was, is the amount of water in the tank increasing at time equals 15? Is the amount of water in our tank increasing at time equals 15? No. The answer is no. I'm going to answer the specific question. I'm not going to say it's decreasing. I'm going to answer the specific question was, is it increasing? And then why or why not, I would cite our, what we just found out about our derivative, right? That the function we defined as a, so a prime of t, was less than 0. Our derivative is negative at that point. Okay, any questions on that? Second question. Let me get over here. To the nearest whole number, how many gallons of water are in the tank at time equals 18? So again, that's our amount of water, right? We're evaluating our amount function for 18. So if I were to write that out on paper, it would look like, just using what we had above for our amount, we start at 1,200 plus however much is totaled up from what's put in versus what's taken out on the interval from 0, and this time specifically up to 18. Now notice I'm not going to plug 18 or 0 into the functions inside. The integral takes care of that for me, right? So this is still w of t minus r of t dt. Don't forget your variable of integration. And again, this is a calculator question, so now I can go to my calculator and I can get all of that typed in just as it looks there. So we would start with our 1,200, and then we have a function on our calculator to do our integration, math 9. We are going this time from 0 to 18. And then we got to be specific to how we type. I typed in my calculator, or you can type it in the long way, but we already typed in w and r as y1 and y2, right? So I can go insert those in here. Y1 is w of t minus y2 is r of t. Notice I am not evaluating them at any particular place because the integral is going to evaluate them at 18 and at 0, right, for me. So I'm not putting in specific numbers there. Otherwise, they would become constants. They are just functions. Hit enter. Now, the number we see up there is 1309.788, but to answer the question, I would have said 1310, right? The question was, to the nearest whole number, how many gallons? And also very important that we are, 1310, labeling gallons. Okay. Yes. Yep. Equivalent. Other questions? We will come back to our calculators. Let me get the next screen though here. Sticking with the same problem, question C. At what time t for 0 is less than or equal to t is less than or equal to 18 is the amount of water in the tank at an absolute minimum? Show the work that leads to your conclusion. Where's your calculator? Okay. So let's talk about this one real quick. Maxes and mins, just underlying concept there, right? Maxes and mins happen at endpoints of a closed interval, so we definitely have to check out 0 and we definitely have to check out 18 because those are possibilities. And they also happen where? It's like a two-word phrase I'm looking for here. Endpoints we already identified. When it equals 0 and undefined. Those are called critical points. But critical points of what? Of the derivative, the velocity function, or the derivative of our amount function, right? So we would be looking for the endpoints, 0 and 18, and we look for critical points of our derivative. So let's remind ourselves, first of all, what our derivative was. We just did that on the last page. You still can see it. I cannot, so I'm going to rewrite it here. Our derivative was w of t minus r of t. We have shown this several different ways, but I can actually evaluate function A at any place, right? We have a function A that I can evaluate at any place, which means we can find the actual values, which is when I would, just make a table of values over here so I can side by side compare all possible places for my maxes and mins. We know on this list are the beginning and end of our interval, 0 and 18. And we're going to check out critical points of our velocity to see if there's anything else that would happen there. So let's look at our velocity function. W of t minus r of t is created of this function minus this function. Let's talk about the undefined part of it first. Of any of these, now I do see variable, or fractions, which always is a little indication there might be something undefined, but the way these fractions are set up, is there any way those are undefined? Nope. Okay. Sine functions are continuous, yes, so those aren't undefined. We do have a little bit of an issue with the domain restriction here, but on the interval from 0 to 18, is that an issue with our square root? No. So, no undefineds as we look through our critical points. Is there some place that this would be 0? Can this equal 0? Yeah, it's going to equal 0 exactly when they equal each other, right? Or if I write it this way, if I were to add that r of t over, doesn't it make sense that they would equal 0 when they equal each other? And if they equal each other, that's called a point of intersection, where you can go do your solving a system graphically where those two lines intersect. Well, guys, we already have it in our y1 and y2, right? So let's graph them and find out where they intersect. And that is kind of a whole nother conversation, because let's talk about how would we graph that. Okay, one of the big things that I will always continue to stress, set your window to the interval that they give us. So I would set my x min to 0 and my x max to 18. I don't want to see anything outside of that would tempt me to be confused or add answers or whatever. So 0 to 18 on our x's. The y's might be a guess and check kind of thing. Knowing what I know about trig functions, the number in front of our trig function is the amplitude when we think about a sine curve. Okay. Now these might have a vertical shift, or the squaring part makes it always positive, those types of things. So, but I always saw that it had an amplitude of 275. That told me that I might need to go a little bit above that. I guessed a window, 0 to 18, and I had -4 in there from earlier. I went up to 300, and we might have to do something greater than that, less than that, but it gives me somewhere to start. And I want to make sure that I'm seeing all of every curve when I hit enter here. Okay. So that's my thought. That was my thought process behind picking those numbers. I know what a sine curve looks like, so I would kind of went off of that a little bit. So when we look at this graph, I can see the top and the bottom of both of those curves all the way from 0 to 18. So it looks like that's a pretty decent window. And so I can see on this interval from 0 to 18, 0 and 18 definitely look like places I would want to check out as minimums. But it does intersect here and here as well, and I need to find out what those x values are. So you let my calculator do that for me. You have that function under second calc. Intersect, it's going to put that little bug on my graph. Just move it closer. Like if I want to find this one first, I would move my bug a little closer to that than anything else. And once it's closer to that, hit enter, 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 and it tells me that that intersection is happening at 6.495. So that is a place where they are equal to each other. I would add that to my table. They have another place of intersection, so I'm going to go there. Get closer to that intersection than anything else. Enter, enter, enter. And that one is at 12.975. And there's my list of possible places that we would have maximums and minimums. Okay, well, it can only happen there because I actually know the function a of t. We have it on my last screen up here, right? We can go evaluate our function at each of these places, right? I just am typing in a 0, a 6.495, all of that. So let's go back here. We actually already have the last one done, didn't we? The last thing we just did on our calculator was evaluating it at time equals 18. So I have that as 1309.788. You can continue to type that in. I have mine right there, so I'm just going to go second entry and change the 18 to my times specific. Oh, if I change that to a 0, from 0 to 0, this is going to be what? 0, right? An integral from a number to itself is 0, which means at 0 we're at 1200. We already knew that. Matches our initial conditions, right? So the only ones we actually need to do is 6.495, which looks like we are at 525.242. And again at 12.975. Okay. So let's talk about, again, supporting my answer with showing my work. Things that I absolutely would show is that I am setting my derivative equal to 0. That explains where these numbers came from, right? And somewhere on my paper that I'm understanding that that's a critical point that's going to show up on my table. That I identified the critical points and my endpoints, found their values, and then we just answer the question, which one is our absolute minimum? Well, that would be the smallest number in that table, right? So our absolute minimum is happening at, see, it says at what time? So absolute minimum at time equals 6.495 hours. And again, a table of values, 100% justification. A sign chart, which we'll see a sign chart again later today, not justification. That is for your thinking process, but not to justify. Questions? Okay, Last question on this particular problem, letter D. For time is greater than 18, no water is being pumped into the tank, but water continues to be removed from the tank at R of t until the tank is empty. Let K be the time which the tank becomes empty. Write but do not solve an equation involving an integral expression that can be used to find the value of K. Give me a second to jot that down and then we will talk. Okay. I rewrote our function that we had created earlier, the amount of water in our tank. And I did it specifically from 0 to 18, over that first interval, from 0 to 18. And we had found out that this amount right here at time equals 18 ended up being what, 1309.788? 887? 788? 788? Okay. And so then they're saying, okay, starting then, as time is greater than 18, we are no longer pumping water into the tank. So if I were to kind of adjust this, we are no longer pumping water into the tank, right? From that integral, we would take out that part. We're still removing water from the tank, and how long is it going to take us then, starting at time equals 18, how long is it going to take us to get to 0? Okay, so we want at the end of this for our amount to be 0. So what we can do is now our time equals 0, if you want to call it that, would be how much we have starting at 18 hours, right? So at 18 hours, we've got 1309,788 gallons. Starting then, as we continue to remove water from the tank, we're basically looking at how long is it going to take if we consider that our starting point. So that's at time equals 18, right? Our integral, as I showed up here, is no longer going to be putting water into it. So as we think about the impact on the water, it is only going to be subtracting the rate of change of water leaving the tank. So our integral will just be of R of t, and you can put the negative in there or subtract the amount of water that will be totaled up inside there. But let's talk about the numbers I'll put on my integral. What interval are we doing that? So what time are we going to start just using our R of t? At 18, right? And they're saying we're supposed to be creating this to be then K is the time that we would be done, right? So from 18 hours until the tank's empty, which is K. And if our tank is going to be empty, yes, this is signaling my amount, right? But what do we want the amount to be, specifically, if the tank's empty? 0. So what I would want to do is make this equal to 0. Okay, questions on any of that? That's one way to show this. It says we're not supposed to solve, so that's all we're doing is setting this up, and that's a very common question on our AP exam as well. Then you just knowing what this is representing and being able to show it, but we don't need to go find it. Any questions before we move on to our second question today? All right, second question. We've got a particle moving along our x-axis. Particle moves along the x-axis so that its velocity at any time t for 0 is less than or equal to t is less than or equal to 5 is given by v of t equals the natural log of t squared minus 3t plus 3. It also tells us that the particle is at position x equals 8, at time equals 0. All right, so very straightforward. The biggest part of this first one is remembering how to take the derivative of a natural log, right? Because we have the velocity, they're asking us for the acceleration. So the derivative of our velocity function will equal our acceleration function. What's the derivative of our natural log again? 1 over the insides. And it's a chain rule on this one, so then you have to multiply by the derivative of the insides, right? So that's where a lot of us are going to forget that part of it. It's 1 over the insides, and our insides are t squared minus 3t plus 3 times the derivative of our inside, and the derivative of our inside would be 2t minus 3. Well, if I multiply those together, multiply straight across the top, straight across the bottom, that's just going to end up in the top here too. So 2t minus 3 over t squared minus 3t plus 3. Specifically evaluated at time equals 4. So again, using my correct mathematical notation to indicate that, I can use that bar, or I could go a of t and show plugging that in. Let's see, 2 times 4 is 8, minus 3 is 5. 16 minus 12 is 4, plus 3 is 7. Check my mental math. Yeah. Any questions on the first part? No label to be had because we're just talking about on our x-axis here. Next one, find all times t in the open interval from 0 to 5 at which the particle changes directions, during which time interval from 0 is less than or equal to t is less than or equal to 5 does the particle travel left. So kind of two parts to this, where does it change directions and when is it traveling left. For the direction of travel, between your position function, your velocity function, and your acceleration function, which one should we be looking at? If I know my position is 3, does that tell me which direction it's traveling? No, it's not our position function, right? If my velocity is 3, what does that tell me? It's going right. It's increasing, right? It's positive. So we should be looking at our velocity function on this one. So on the interval from 0 to 5, it is going to change directions, potentially, when it's going to hit our x-axis or when our velocity function is 0. So remember, we're going to look for our critical points of the velocity function, right? Of this velocity function, natural log of t squared minus 3t plus 3, is that ever undefined? Not sure, but I do think there are places that it is 0. So let's start with the zeros part of it. Okay, if we look at this zeros part of it, if I set this equal to 0, also is going to be equally kind of confusing, but we might at least have a path of how to attack this. How do I start solving a log equation? I would flip to exponential, right? When we've got our logarithmic equation by itself, I would flip to exponential, and exponentially this would be e raised to the 0 equals what's inside, yes? Okay. Okay, well, e to the 0 is 1. Okay, solving that, I would get it equal to 0. Okay. Are there factors of 2 that add up to -3? Please say yes. Yeah, -2 and -1, right? So it looks like we would have zeros at 2 and, at 1. So going back up here, remember this sign chart is just for my visualization. From 0 to 5, it looks like we have zeros at 1 and at 2. And what we want to know is what's going on with our velocity at those times. So I pick something in there. Grab your calculators. Let's pick something between 0 and 1, like a half. And evaluate that function up there. The natural log of 1/2 squared minus 3 times a half plus 3. I don't need a number, I just need a sign. Positive or negative? Positive, okay. Pick something between 1 and 2, like 1.5. Positive or negative? Negative. And something between 2 and 5, like 3 or 4. Positive, all right. This is just for me to kind of visualize what's going on. This is the value of my derivative in those intervals, and it tells me what my function would be doing. Positive slopes here, which means my function would be increasing. Negative slopes here, my function is decreasing. Positive slopes here, my function is increasing. Or moving right, left, and then right. So the first question is, find all times which the particle changes directions. So changing directions. Now, it didn't ask us specifically which direction, which is going to impact how I justify this. Changes directions at time equals 1 and time equals 2. Why did I say that it changes directions at those times? Because my velocity switched signs, right? So I would say v of t switches signs. Now, the reason I said it didn't ask me which direction it was changing impacts the justification, because if it was specifically supposed to be changing from moving right to moving left, I would have to say that my velocity changed from positive to negative, specifically, right? But just changing directions is just changing signs on my velocity. Second question, when does the particle travel left? It travels left from 1 is less than t is less than 2. Why? My velocity is negative. Always supporting every answer with a justification, even if it doesn't ask us, because it's not guaranteed that they're going to ask us every point that they evaluate for. Times on right here. Yep. Because at 1, it should be stopped for a tiny moment. So I would not put that at equals. Because if they had asked me the question is when is it stopped, I would have answered at time equals 1. Other questions? Okay, we have 2 more questions real quick on this one. Okay, find the position of the particle at time equals 2. Find the position of the particle at time equals 2. I'm going to let S of t be the position function. Okay, which means S of t is the antiderivative of v. And how do I show that I want to take the antiderivative of v? An integral, right? S of t is going to be the antiderivative of v dt, right? And this particular problem, they're asking us to evaluate S of 2. And so if I want it to be S of 2, I would go from time equals 0 to time equals 2 on our integral here, right? And you'll notice that I left a kind of weird space between that. Why? I left room for something. The initial conditions, right? We aren't starting at 0 because this is going to tell us how far we move, but we started at 8. And we're going to move this much and end at, I don't know. Something my calculator will tell you. Actually, your calculator will tell me. I don't think it goes far, only because from 0 to 1 it was moving right, and from 1 to 2 it was moving left, so kind of move back and forth in there. What are we getting? I think that's right. Okay. And then the last one, find the average speed of the particle. Now, average speed, remember that speed equals what function? Velocity, but absolute value, right? So the speed of our particle is going to be the absolute value of our velocity, and it's asking us for the average of that function. So the average of a function is that formula that says 1 over b minus a times the integral of that function from a to b, right? Remember that formula? And we are doing this on the interval from 1 to 2. So our b and a would be 2 minus 0, 1 over 2 minus 0 times the integral from 0 to 2 of, and speed, so I'm going to put in here the absolute value of our velocity function dt. That is how we find the average of a function. 1 over the difference in your integral times the integral from a to b. When you type this in, do I have to type in the absolute value? You do, because speed is always positive, but on the interval from 0 to 2, velocity is actually negative from 1 to 2. And we get 0.371. Any questions?